Dr. Harry Kroto, Sir Harold Kroto, actually, he's been knighted. I met him just briefly, in fact, in the Netherlands, and I first saw him give a presentation at the Bridges Conference in Enschede, and then I saw him give a presentation in Delft at the Symmetry Conference, where I was giving a paper myself on my golden section topic. But I was extremely impressed by both Harry, Dr. Kroto, and his wonderful wife, Margaret. And during a session in which they were building these geometric models on the town square in Delft, I saw how beautifully both of them work with young people. And that's one of the big things about both Dr. Kroto and his wife, Margaret. Margaret, we're going to introduce Dr. Kroto. Margaret, would you stand so they at least see you? Let's give her a big hand as well. Now, Dr. Kroto is presently at Florida State University. He's the Francis Epps Professor in the Department of Chemistry and Biochemistry. He's a co-recipient of the Nobel Prize in Chemistry for 1996, along with two others, Richard Smalley and Robert Curl, who were at Rice University at the time. Dr. Kroto was at the University of Sussex. Dr. Kroto discovered, again, I don't want to go into his lecture, but I want to clue you in a little bit ahead of time. He's the one who discovered, along with some Canadian radio astronomers, these long linear carbon chains in interstellar space. And then in 1985, using graphite heated with a laser supersonic cluster beam, they recreated these flexible molecules, these carbon chains. And they discovered these perplexing stable spheres. And again, we'll let him talk about this. And one of them in particular, carbon-60, they eventually named the Buckminsterfullerene or buckyball, because Dr. Kroto had recalled the geodesic domes of Buckminster-Fuller, so they were giving him credit or some credit for it. It's interesting, when he went to Florida State, one of his colleagues said, quote, "The plan is for him to give at least one lecture to every freshman at Florida State during his time there." Some of you may have noticed the last time the Florida State football team played wasn't the greatest result for Florida State, but if you watched at halftime, who did they honor? It was Sir Harry Kroto, because he's available to the students at the university there. And so it was beautiful to see within the sports field someone from the science realm who really is a wonderful human being. Let's give Sir Harold Kroto a big hand for being with us.
Pleasure to be here in Ocala, or is it Ocala? Anyway, thank you very much for that very nice introduction. Well, it's chemistry in nano and outer space. So I'm going to take you into space, but also into modern nanotechnology. And the first thing I'm going to say is that science is not common sense. For instance, there are three senses. One of them is to switch on things. And the three senses, the first is common sense. Now, common sense tells us that the sun goes around the earth. Who agrees with me? It was over here this morning. It's over there, common sense. Okay? Now then, it's uncommon sense that tells us the earth is turning on its axis. That makes it seem as though the sun is going around us. is the uncommon sense and bravery of Copernicus, Galileo, and Giordano Bruno. Copernicus had the good sense to die before he published this. Galileo was threatened by the Inquisition and said, no, all right, the sun goes around us. And Giordano Bruno said, no. He said no, and they burned him. So, 500 years ago, any of you in this audience who insisted that the Earth goes around the sun would have been burned to death. How about that? It's interesting. Okay. Nonsense is common now. Okay. Let me tell you my take on science. Aspects of science. Well, the first is that it's a body. Can you hear this? Okay.
Yeah. Since you're turning that way, I'm going to move it over to the side.
Because I've got a... Okay, can you hear me better now?
Yes.
I'll try and get it to him. Okay. The body of evidence-based knowledge. This is what you learn at school. There's the application of that knowledge, technology. And then the way in which new knowledge is discovered, scientific method, research. They're different. But there's something more important. It used to have another name. It was called natural philosophy. And for me, the most important aspect has been forgotten. And that's this. That is the analytical construct to decide whether something is actually true with a significant degree of reliability. I hope you agree with me that truth is important. Okay? And the ethical purpose of education must involve the teaching of young people how they can decide what they've been told is actually true. We should be telling our children this. And thus the teaching of a skeptical, evidence-based assessment of all claims, without exception, is an intellectual integrity issue for all teachers. Now, Pasteur, the famous scientist, said, in the fields of observation, chance favors only the prepared mind. Well, what did he mean? He means education. Well, believe it or not, that's what I used to learn. I know it's hard to believe. And as a kid, I didn't want to be a scientist. What I really wanted to be was Superman. And you want some evidence? Here it is. But I couldn't fly. So I did other things. I did gymnastics, okay? And played tennis. We got to the finals of the university championships a couple of times. And I acted in a play, Henry V. Now, I'm the handsome guy on the right. I'm going to blow this up. And I tell young people, don't become an actor. The guy in front became an actor. And he is now 5,000 years old. I'm a bit younger than you. Okay. We don't age so fast. Ian and I were in the same year. And actually he came out to Tallahassee. And he went to the magnet lab. I took him to the Magneto, ought to go to the magnet lab with the most powerful magnets in the universe. Anyway, here he is on this visit. He'll stay with us for a few minutes. I had Meccano. Some of you may have had erectus. How many of you had erectus? Everybody over the age of 500. I made things out of this. And I think it's important. This is called Meccano in Britain. And in those days, these are the ads, but they're not violent and destructive. Meccano boys, and of course today you've got to add girls, are keen, ambitious, and inventive. No boy or girl who follows the Meccano hobby can be a bad boy or bad girl. And I think it's important to realize that we made things with our hands with nuts and bolts. I also had a camera, and I want to show you what it was like to take a photograph. And some of you may recognize it. How many of you had a camera a bit like this? Yes, the same group of people. And of course, what was it like in the old days? Okay, where you opened it up, put the film in the dark, and you had to set the distance and the exposures, start and work all this stuff out, how much light was falling on the whole thing. Okay, the speed of the shutter, take the film out, put it in a development tank, pour in the chemicals, fix her, hang it out to dry. Then you had to, that was the negative, you had to print it out. And you had to do all that to get a photograph, okay? And you had to have a very good incentive. And I did have one, and she's in the audience now. Today, all you have to do, basically, is that. And you've lost so much. How many of you know what's going on inside the camera? You've got the pictures, but I knew everything about the process. I learned chemistry, I learned about light, I learned about reciprocity, failure, and all these things. You have other abilities, but you've lost a lot without modern technology, and I think that's a bit of a problem. I also collected things. I collected magazines for nothing in tourist agencies. Beautiful works of art, okay? All these, in fact. I think that's Franz Arkentin. Some of you, the older people, will remember that. Fantastic quarter. So I have a big collection of all these things. I was interested not just in science and tennis and other things, but also in graphics and art and design. And these are some of my work. In fact, when a kid, I was drawing airplanes, as kids always do, cars. I did posters, brochures, poster, another one that was on the underground. Look, I was art editor for the student magazine at Sheffield. That got into an annual of graphic design. And in fact, that's my book. If you want to buy it, it's out of print. Okay. And my first award was for this. And I used to look like this. Now, some of you youngsters are young and beautiful, but you're going to look old and decrepit like you. So, enjoy your youth and beauty while you may. It does not last, I guarantee. Okay, so these are some of the sorts of things that I still do. I do a lot of logos as well. I like logos. This is the Kroto Research Institute, where the R is dropping something into a test tube. Conference on the population explosion. Breakthrough. I designed this stamp for the UK. Inorganic biochemistry discussion where we've got d orbitals and leaves and flowers. And this is for my wife, who's essentially fluent in French. Association Française Tallahassee. And I like this because the F isn't actually there, but you can see it. And so these are the things that I still do. Oops. So that. Mr. Gates again. I thought I'd show you the development of my favorite logo. I did a workshop for small children down in Australia on the internet. And I thought I'd do a little logo for them. So I was in a restaurant, and on the napkin, I started to doodle, and then ended up with this koala bear on a buckyball. You might think it's a soccer ball, but it's actually a football. Okay. All right. Now then, I don't expect you to solve that equation, but that is the fundamental equation of angular momentum in quantum mechanics. Now, many of you will know that Newton really developed the basis of classical mechanics and understood why the Earth goes around the Sun with gravitation. That equation is the equivalent equation which applies to atoms and electrons going on. And science was born when people like Galileo recognized that mathematics, and particularly algebra, was the fundamental language of the universe. And he said, unless you know mathematics, you will not understand a single word, and you will wander through a dark labyrinth. That doesn't mean that you have to do algebra, but it means that some of the most elegant and beautiful and simple things will be not so easily understood. They say, if you can't explain it to your grandmother, you don't understand it. It's not true. How many of you like mathematics? There you go. Well, you know something, and you love something that many people don't. And you will understand some things that are not understandable without it. And some people appreciate this. For instance, here we have the Dirac equation and the Heisenberg energy equation. Actually, there's a mistake here, and there's a minus sign. That's Maxwell's equation. DNA, the Heisenberg uncertainty principle. That was LSD, just in case you want to know. My favorite is this one. Nicole, a physics graduate student. My tattoo is a Taylor expansion of sine. I consider it the most beautiful thing I have ever learned. Now that's incredible. That a student says an equation is the most beautiful thing they've ever learned. So there is something there. And just as, say, if you're deaf, you can't appreciate Beethoven, Mozart, or the Beatles, or Jefferson Airplane. So unless you delve into mathematics, there's something. It's not necessarily important, but it will be something that I'm afraid I can't help. It's not my fault. It's not my fault that the universe speaks in these mathematical forms. Anyway, there you go. And we met her, believe it or not. And I managed to get the end of that equation. Now, Van Vleck was a famous scientist. 2 times 3 is equal to 6, and 3 times 2 is equal to 6. But in the quantum world, things can happen that are not so obvious. For instance, A times B is not equal to B times A. And I thought that was interesting. And if you want to understand light, seeing, in fact, it was only in the beginning of this century that people realized that they could not understand color. You couldn't understand it. And that would require quantum mechanics to come along. If you want to understand the light coming from here, then you have to do a bit of this. And in fact, Van Vleck said, practically everyone knows that the components of total angular metal or molecule relative to x, y, z fixed in space satisfy this relationship. Well, when I came here, I stopped at the first gas station and I asked everybody, did they know this commutation? Not many did. But anyway, I'm going to give you a little bit of a slice of why mathematics can be so enlightening. Of course, the Earth orbits the Sun. We use classical mechanics. And for electron orbiting a nucleus, we use quantum mechanics. Now, we go to this equation, and what you find when you look into it in detail is that the electron is spinning around the nucleus. And there's something called a quantum number. Very simple, J is not 1, 2, 3, 4. Okay? And that it indicates also that not all orientations are allowed. Only certain ones are allowed. You go back to the equation, and you discover there's a very simple equation called 2j plus 1. When j is 0, 2j plus 1 is 1. That's not too difficult. When j is 1, 2 plus 1 is 3. When j is 2, 2j plus 1 is 5. Okay? That's the hardest equation you're going to have to deal with. All right. Hence, we put some boxes, 1, 3, and 5. Now, I'm going to double that set, double that set. Move this to there, and that to there. Double that, double that, double that. Move this to there, and that. And what have we got? A periodic table. Fantastic. Based on the numbers 1, 3, and 5 coming from that equation. Can you see why it's beautiful? Because the periodic table explains the whole of chemistry, Mendeleev's periodic table, all of life, and all the useful bits of physics, if there are any. Okay. Of course, physics is that overarching subject of everything in the universe. But chemistry is that big part of physics, which applies to us. The chemistry in your body, things like that. And that's it. And it's based on numbers 1, 3, and 5. Fantastic. And it comes from that equation. And that, for me, when I evaluated and went through 2 or 3 pages of algebra together, it was such a cathartic moment. And it's that sort of thing that you get. Okay? And I hope I give you a little bit of, if you're not mathematically, a little bit of a feeling for why it can be so beautiful. All right. Now, my favorite molecule is not the C60. It's actually this one, nitrosamine, because it looks like it. Does it look like anything to anybody? Yeah, it's my dog. Okay. Blue, red nose. My dog, look at the spectrum, it shakes its head and looks at this tail. Not only that, my dog can do other things as well. It can undergo what's called internal rotation. It's hydrogen, nitrogen, carbon. It's been drinking, and if you're a dog, you've been drinking, and you know what you desperately need is lactose. I show you this because molecules are flexible. The key thing about nanotechnology is not that they're very small. Of course they are very small. But because they can do things. Because molecules can act like machines. And that's very interesting. Now, this is carbon dioxide. And it's vibrating. And the reason that there's a greenhouse effect is because of the vibrations that as the heat from the ground comes off, the more CO2 can absorb it and start to vibrate. You get the idea? Like pushing a screw. That's the situation. And originally I was interested in long carbon chains molecules. And the spectrum that started the ball rolling was the spectrum of this molecule. And it was synthesized by my colleague David Walton, my close friend and colleague. And here we are. And David had made a chain of 32 carbon atoms. That was fantastic. No one had done anything like that before. And what he did was he used copper to take out water, a couple of catalyzed oxidative carbon, to couple these carbon together. Okay? That's all. And we made that molecule. Now, about the same time, radio astronomy and infrared astronomy was coming on. Now look at the stars. You see on the left and the right in the optical range. Okay? Left and right. But that one is not there. In the infrared, that star is inside that black cloud. That is a totally dense black cloud. And the star is a new star that has just been born. And you can see it in the infrared because infrared can get through. Radio waves come through, low frequencies come through the clouds. But light is a high frequency, you cannot get through. Okay? So you can't see the sun today, but you can still use your mobile phone, unfortunately. Anyway, at the same time, radio astronomy discovered a molecule with 3 carbon atoms, shown here, in Sagittarius. And one of my colleagues, we were postdocs at the same time in Canada, Japanese scientist, Takeshi Oka, was doing some radio astronomy. And I wrote to him, and he wrote back, "Dear Harry," he said, "thank you for your letter. Yes, exclamation mark, exclamation mark. I am very, 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 very much interested in your molecule. The same number of berries as there are carbon atoms." We got together and we detected it in its interstellar space. So here is a picture of Canada, the telescope in the middle of summer. And see, I guess you guys from Minnesota know what I'm talking about too. Okay, it's a 46-meter dish. And if a molecule rotates, and it has a dipole moment, you can give out a photon, you can detect it with the radio telescope. And what we showed was that there were carbon chains in the space between the stars, with 5, 7, and 9 carbon atoms. So what was going on? Well, the first thing, we were so excited that we had our photograph taken. Okay? I used to have some hair, and it was blackish. I don't think Lorne ever had any hair, actually. But there's Takeshi, Norbert, and John. And we showed this, and the chemicals were discovered thanks to Canadian work in radio astrology. I hope you know the difference between this and that. Anyway, there you go. Now, I thought I'd show you something by one of my favorite friends and lecturers.
I've told you, and you have to believe it, I tell you the truth, that carbon monoxide is the second most abundant molecule in the universe. And yet, our theory, our equilibrium theory, says there shouldn't be one molecule in the whole universe. It's that extreme. What does this say? Well, it doesn't say that thermodynamics is wrong. Of course it isn't wrong. That's impossible to be wrong. It says that it's totally inapplicable to the chemistry of the interstellar medium. That everything is dynamic. That in a sense, it very much resembles the Earth. If you ask, what is the equilibrium status of everything is quiescent, everyone's dead. That's it. And very uninteresting. So we would like something much more dynamic than the thermodynamic equilibrium. And I should say, as a testimony, really, every time I mention that to a group of college students, the audience breaks into tremendous applause if thermodynamics is not applicable. And I wonder why. It might well be that it's so poorly taught that just like it.
Those of you taking thermodynamics will know what he's talking about. Anyway, that's Bill Clinton from Harvard. Now, when we discovered that, another star was discovered by Eric Beckman and Jerry Nogebar. And here is a fantastically powerful infrared signal in the sky. It's off scale. And it's 10 times stronger than any other star in the infrared. It was a red giant star, which blew off its outer shell, 15 kilometers per second. And this is it. The star has a shell about the size of the solar system, and it had carbon chains in it. And that star was the trigger for the next part of the story. And I'll digress a little bit, because in 1967, I'd been to Expo, and that turned out to be very important. Bob Curl had invited me to Rice after a conference, and it told me to go see Rick Smalley. Rick Smalley had developed a fantastic apparatus for vaporizing metals, such as aluminium, to produce clusters. And once he was in this, I thought, well, why don't we change the aluminium to graphite and try and produce the carbon chains and simulate the conditions in this star? That was the simple idea. Just vaporize the graphite and get the carbon chains. That would detect it. That's what we did. As the plasma produced going through into a mass spectrometer. And Jim Heath, Sean O'Brien, and Yuan Liu were the great students that were involved with this. And what we discovered, that was an incredibly strong signal for a molecule with 60 carbon atoms. I put 60 plus question mark. 60 huge and C70 also. And the clue for me was in a Graphis edition devoted to Expo 67. When I was a student at Sheffield, as a student, I discovered this magazine, Graphis. It's the most important magazine in graphic design. And the Expo 67, some years later, was all about it. And on a particular page was this picture. And this picture was in my mind. Once you've been inside this building, you're there. And this building has a secret. It looks as though it's all made of hexagons, like graphite. But it has a secret, because just there is a pentagon. It turns out you need a pentagon, 12 pentagons, to make a socket. You can't make it with just hexagons. You need 12 pentagons and 20 hexagons. So that was the story of that. Oh. And that's how C6 turned out. Okay? Well, it was quite an interesting thing, because no one had thought of this model. Well, a Japanese had thought about it, but nobody thought it was self-assembled. It was incredible. And that was the biggest and most important aspect. And there's a whole load of foolery in chemistry. Okay? Just a little bit, just to give you a little bit. You can put molecules together with ferrocene, you can put fluorine on it, and you can put phenol groups on it. You can do a lot of things. And there are about 1,000 papers now. Oh, 20,000, 1,000 a year papers on the chemistry of the C60 molecule. Well, then nanotubes turned up. How many of you heard of the nanotubes? Okay. Well, they're carbon tubes. And if you look under a microscope, what you see is a cross-section. So here we see a cross-section. This has got 3, but this one has 5 walls, okay? Now, some cases, you see them closed off like this. So I thought maybe there's a metal particle in the center, and that metal particle has carbon in it, and maybe it will produce igloos like that if the carbon can come out of the metal and form a little dome like that. Okay? That was the idea. Now, my colleagues, Mauricio and Umberto Torron, working with Florian discovered that that was actually quite right. Because here is a metal particle inside in a cross section, and there, if we look at these pictures, there is a line of carbon coming out, and here you see whole sets of these tubes coming out. And with a bit of luck, we can see this in the time-lapse picture, okay? Under the electron line. This is a metal slope. These are nanotubes. Now watch what happens here. Suddenly, out come these tubes. These are nanotubes being born. Okay, so you've seen a nanotube. Now, what's the big challenge? Ooh, something like that. The big challenge is something that I don't know will ever be achieved, but it might be. We have to be able to make our nanotubes all the same diameter and all as long as possible. Why is that? Imagine you have a box of straws, okay? Paper straws. And you glue them together with a very weak glue. Then you can stand on the straws and they will hold you up, okay? That is the way to make paper straws. Now, what we have to do is take them all the same diameter so they fit perfectly together. Perfect hexagonal packing, weak, say, post-it glue, and it's intrinsically very, very strong. You wouldn't believe it, but just try it. Now, nanotubes already have the glue. They're called van der Waals forces. But the problem is making them. We need a bundle of 10 to the 15. That's 1,000 million of them. All right? And we can make a bundle of 20. And we can only make them a few microns long, maybe a millimeter or so. We need to make them feet, or meters, or kilometers long. If we can do that with a fantastic material, it will be about 100 times stronger than steel and 1/6 the weight. Now, why is that? It's not that steel is not strong. It's that steel cracks, okay? Metals crystallize, and so you propagate a defect through the crystal. If you want to cut a tree down, you cut through halfway down, you push it up. You create a defect, a weak spot, but you can put all the force in that one spot. You get the idea? That's what happens with all materials. All materials are intrinsically weak because of defects, where you put a macroscopic force at the microscopic point. This stuff will solve that problem, as trees are solved. Trees are solved because they have these fibers, right? So it's very strong this way. You can't push a tree over without a massive trouble, okay? You can split it down the circle. These nanotubes have the same thing, because a defect in one tube will not propagate to the next. Get the idea? That's the difference. Okay. And here, Florian, and there's Mauricio. This is something. And I like to show this picture because it tells you something about science that doesn't apply to anything else, essentially. And that is from Syria, India, Mexico, Taiwan, Holland, UK, Spain. Scientists, in general, is the same in Japan as it is on Mars and here in Florida. So we are all looking at the same thing. And I think it's important to realize that the scientific community is probably by far the most international of all. And I think I love this picture because it shows it. I came to Florida 10 years ago, and I thought I'd show you my colleagues here. Steve came from the UK, Darryl, our Swedes, Prashant from India, Nicola from a visit from Italy, and Paul Duncan. And this guy, well, that's Paul Dirac, considered to be an equal of Einstein. Well, you've not heard of him because he's a very quiet fellow. He never comes into the lab. He sits outside in the sun, and I put my hat on to keep it visual. Comes to the last things I want to talk about. When I was a kid, my name was Kroto, and I was 7 years old. And it said, Miss Barker thinks I better write and tell you that we are not at all pleased at the way Harold, that's me, has been working during the last few weeks. He is very fond of play. Well, that's very interesting, because here's Richard Smalley, one of your great physicists.
So I decided I'm going to do things only for the fun of it. And only that afternoon when I was eating lunch, some kid threw up a plate in the cafeteria, which has a blue medallion on the plate, the Cornell sign in the cafeteria. And as he threw up the plate and it came down, it wobbled and the blue thing went around like this. And I wondered, it seemed to me the blue thing went around faster than the wobble. And I wondered what the relation was between the two. See, I was just playing, no importance at all. So I played around with the equations of motion of rotating things. And I found out that if the wobble is small, the blue thing goes around twice as fast as the wobble goes around. And then I tried to figure out if I could see why that was directly from Newton's laws instead of through the complicated equations. And I worked that out for the fun of it. And this rotation led me to a similar problem of the rotation of the spin of an electron, according to Dirac's equation. And that just led me back into quantum electrodynamics, which is the problem I've been working on. And I kept continuing now to play with it in the relaxed fashion I had originally done, and everything is just like letting a cork out of a bottle. Everything just poured out. By the way, in very short order, worked the things out for which I later won the Nobel Prize.
Now, I think that's important, because if you found your position in life, then the work becomes easy. It's hard work, but it's a lot easier if it's a bit like play, okay? And it's not just in science. Ian McEwan, one of our great English writers, who was at Sussex University, is in this interview.
Where do you write? How do you write? What's the process?
I have a very nice study course. I've found that one of the most freeing things you can do as a writer is to describe the novel which you're never going to be bothered to write. You have no burdens on you. Or you write the opening sentence to a novel that you're not going to write. You feel completely free. And sometimes I've written myself into a novel that way. I started Atonement that way with a careless sentence and then a paragraph. And then thought, well, maybe there's something here.
To be creative, you mustn't have a burden on responsibility. It's very difficult today, but nevertheless, it's something to think about. Like this little boy. This little boy, photographed by Margaret here, is not thinking about passing exams, not thinking about a job, not thinking about a prize. And I was playing around, like this little boy, trying to make a small fullerene, cage mark, C32. I was just playing around on our coffee table one Sunday afternoon. And I made this, and it wasn't C30, it was C28, and I said, wow, because we had a very strong signal for C28. Turns out there are other molecules, and C28 turns out to be a very interesting molecule. And now I'm going to show you some pictures from Delft, which you talked about. Margaret took some fantastic photographs. We were sitting at this table, and on this table was a buckyball. And little kids like this one came up and said, can we have one of those? So I said, yeah, you can have it, if you make it. Okay, so they sat down. This kid, his tongue never, he made it. And his sister, she decided she was going to make it. And this little kid came along. These kids are tiny tots. But the first customer was this little girl. And I'm going to show you this set of pictures. Just watch this. Totally absorbed. No one was helping her at this stage, okay? She just put the whole thing together. And when it was finished, we didn't know what we got until Margaret downloaded this onto the computer, and it ended up with this picture. Look at that. Isn't that fantastic? That is what it's all about. That is what education is about. That is what to get kids totally engrossed, to make something, and then be overwhelmed by the beauty of something that they themselves have created. Uranium C28, very interesting species. We found that it is a very, very strong signal. It's that strong signal there in the mass spectrometer. And here are my colleagues in the MAG lab who are involved with that really good set of studies. I'm going to finish off with a puzzle that's been around for 90 years, still not solved. When you look at a star with a telescope and a spectrometer and a prism, you get the colors of the rainbow, okay? Colors of the spectrum. But you also get these absorption beams. You see those? And they have been seen for the first time in 1923. In 1936, it was clear that they weren't in the star. They were in the space between the stars, in interstellar. There was something in the space between the stars. It's not dark matter. We can see these. It's in, okay. And we've been seeing them for 90 years. And they're called diffuse interstellar band, DIBs. And here are some. Now, when C60 turned up, I thought, maybe C60's out. I used to call it the third man. Why is that? Because there's graphite in pencil lead and diamond in carbon's diamond. And this is the third one. And suggested that maybe C60 in space has things stuck to it, such as sodium atoms, and that you get what's called a charge transfer. Light can come in and be absorbed, and the charge can jump from the sodium to the C60. And in outer space, I wonder whether it is that. All right. There's a film called The Third Man. How many of you know The Third Man? Well, a little treat for you. I'm going to show you a bit there. Dutterman, Orson Welles. Okay. And it seemed to me that C60 was always there. It was lurking around in the dark solar streets of the galaxy. Okay. Well, here's a bit of film.
What kind of a spy do you think you are, Satchel Butt? What are you tailing me for? Cat got your tongue? Come on out. Come on, whoever you are. Step out in the light. Let's have a look at it. Who's your boss?
Oh, sorry about that. Oh. I'm sorry, it doesn't have a time limit.
you are, Satchelfoot? What are you tailing me for? Cat got your tongue? Come on out. Come out, whoever you are. Step out in the light. Let's have a look at it. Who's your boss? Harry.
He's disappeared. You can see the rest on YouTube. That's one of the most famous scenes in film. Those of you who will always remember that particular scene. Anyway, I thought the C60 is the third now, lurking in the galaxy. And in 2010, the Spitzer Telescope, shown here, produced a remarkable result. It's the white curve which you see here. The red is C60, and the blue is C70. All the lines are there. There are stars blowing out C60. All the carbon in your body was created in a star. What happens in the sun is that 4 hydrogen atoms are squeezed into helium. And the helium has a little bit smaller mass than the 4 hydrogens. And by E equals mc squared, smaller mass means the energy. So that's keeping us warm. When the hydrogen's used up, helium-4 is 3 of them are squeezed into carbon, mass 12. And it looks as though these stars are producing C60. So you may well, your carbon atoms may once have been C60. So C60 is ejected in large amounts from stars like this. Well, it was a film made, it was on Nova, but it's made in the UK by the BBC. And this is Wolfgang Kretschmer, a friend of mine, great scientist, who actually was one of the key people who extracted C60. And I'll show you the last bit of film here.
I believe it is there. And it would be rather nice to feel that, in fact, we were on the right track. There are some interesting features in space, and C60 certainly can fit them better than any other proposal that has been made up to now. I'm a believer, and I think ultimately we'll find that it is there.
But others have said that C60 is nothing like a match for the depleted star.
They're wrong.
Thank you very much.
Okay, we finished nice and early actually, so we would have some time for questions? Yes. So we've got a couple people. Daryl Riley over here is a mic, and then Andrew Jenkins has a microphone over here. So raise your hand if you have a question. The mic.
Hi, my name's Jack. You hear me okay? And I'm just wondering, you seem to be someone that praises at least an interest in a lot of different subjects to be not only creative, but I guess
You have to pull things together.
yeah.
I mean, I think if you're at university, that's the best place to explore other aspects of your potential. And when I was at university, I played tennis, I did posters, I was art editor, made the covers of the magazine, I did my research, and I was interested to do as much as I possibly could. I felt I could play a sport, so I worked as hard as I could at tennis. I was always keen on art and graphics, and I didn't want to miss that. And in fact, I often thought I would have gone into graphic art and design. I was interested in architecture. I'm going to talk about this thing tomorrow, actually. I'm giving a talk tomorrow at midday for the students in here. So I think take advantage of university, because it's much easier to test the water there than it will be when you leave and you go out in the outside and have commitments. So I really did a lot of that. I painted murals. I became president of Athletics Council, so I did a stint of student politics and decided I never want to be a politician as long as I realized how difficult it was. I mean, you're always compromised. I learned that very early, and I guess someone has to do it. And but if you have commitments as a politician, or you have convictions, it's very difficult. Very difficult.
Thank you.
Okay.
We got one here.
Good evening, my name is Carly, and I wanted to ask you if you have ever thought about mentoring students that want to pursue...
Mentoring.
I do that. I've been doing that for years. I mean, I wasn't always a Nobel Prize winner. And so I taught at university. And in fact, my last PhD student just graduated. He's graduating at the moment. So yeah, I was personal tutor to many students. And I give talks around the world and advise. And in fact, just to give you an example, I was in China, and a student wanted some advice on his research project. So I sent him some advice by email, and then he asked me for a reference. And I said, I'll do a reference if you do a recording on your research, because I'm going to talk about that tomorrow. I have a program called GeoSet. Actually, I just wonder whether it's on here. It may be of interest to look at this. And what I'm doing now is, in some sense, is mentoring students. No, it's not there. Okay, I have to get out of this and go to. Maybe it's in this one. What I'm trying to do is get students to make recordings on their projects, and helping them. And at FSU we set up a GeoSet program. Here it is. Okay. If you look at this, geoset.info, we've got a whole load of students, and here is one of them. And so, although I no longer have students, I'm getting students to record.
Here are the Beatles. George, John, Ringo, and Paul. We all know their music, and most of us even know of their impact on the world today. However, whether we realize it or not, we've had more contact with another type of beetle, and they have had far more influence on our very lives. I'm talking about these beetles, the insects. And this presentation will be all about the wonderful world of beetles.
And for teachers, it's a great way of assessment. Instead of marking, I sit at home looking at these videos but the fantastic advantage is Kerry got a Fulbright, Steve got his Rich Media Award, Project got 4 tenure track offers, and they could see she could teach. Brisley got into medical school. Ashley's got a gubernatorial scholarship, my students. Jennifer got into vet school, got a Goldwater scholarship. he got into NHK because he got Japanese. And this is the most interesting. It's an Indian student in Japan who made a recording on our GeoSet. Remember GEOSET? Okay. Look it up on Google when you get there. And she's now got a job at the university back in India. She didn't have to go back for an interview. We can give you effectively an interview via the internet. So that's my mentoring technique at the moment. Okay?
So you see why I wanted...
You're going to set it up here, aren't you?
Exactly, but you see why when I was in the Netherlands and I was exposed to what you do with students, why I really, really wanted to bring him to our college. It's incredible what you do with your students. But don't pull them all away from University of Florida. They don't know what Alden would have this year. There's a question over here.
Sir, over here. Have you thought of using graphene as a base to grow the macrotubules on? That way you could polarize it and allow it to grow?
No, I only do things that I'm particularly interested in. There are lots of people working on graphene. I've never jumped on anyone else's bandwagon. They've jumped on mine.
That's true.
I found that I can't get interested in things just because they're important. I just get interested in things because they're interesting to me. And in fact, the experiment that led to the Nobel Prize was, I would say, before we did the experiment, the least important experiment I've ever done. You can never predict. It was interesting to me. It wasn't even particularly interesting to my colleagues. It took them 17 months to do it. So my view is you can't be satisfied running after the crowd. There are 100 people working on it. You've got a 1% chance. If you're working on your own thing, you've got a 100% chance of doing something which you yourself. And I think that's the only way to be creative. But it's a very interesting area. But I'm now really focused on the education program.
Hi, my name is Danielle. First, I'd like to compliment you on having such a great sense of humor and a warm personality for someone that's pretty much changed the world with their discovery. And my question is, what are some uses of carbon-60?
What are some uses of carbon-60? Some uses.
Oh. Well, it actually doesn't have any uses. There are one or two cases where it seems to be a possible medical application, as just mentioned, but that hasn't yet come in. People are looking at it. The most likely possibility is as a sort of dopant in solar cells. It's a very good electron trap. And in a solar cell, you have to separate charge. And if you trap the electron on C60, it's a good way. So that's the most likely one at the moment. And the most important aspect of the discovery is that we did not realize that carbon could do this spontaneously. And so what it did was revolutionize our views on nanotechnology, and particularly the bottom-up assembly, as you assemble things bottom-up. Top-down is how you make today's transistors. Bottom-up is the next generation of molecular computers. And in fact, we know we can make something like a brain, because your brain has been made bottom-up, assembled from proteins, bottom-up assembly. So it's really a long, long way to go.